Okay, so there are a couple steps to solving this problem. The first one is to look at energy. So we have a bunch of assumptions that make energy work really nicely here. The ball rolls without slipping. We don't lose any energy, as even stated in the problem. So it's obvious we need to use energy here. So first, let's look at the kinetic energy that the ball gains. And the kinetic energy is all being gained from the loss in potential energy because the ball starts stationary. So we know that our change in gravitational potential energy is equal to m times g times delta h. In this case, equal to 1 times 10, since we can assume g is 10, times -1, because we're going down 1 meter, equals -10 joules. That's our change in potential energy, and it should make sense that it's negative because we're losing potential energy. Next, we need to calculate our kinetic energy, and this equation is a bit more complicated, but hopefully you remember the equation. Kinetic energy for a rolling object without slipping is equal to 1/2 mv squared plus 1/2 I omega squared. Now, we should calculate I really quickly. Remember that for a solid sphere, like in this problem, I equals 2/5 mr squared. And I won't do the full calculation here, but you can plug in the numbers and get that this is 0.016. So we can plug in all of our numbers here, right? And we get 1/2. I'm going to pull out the 1/2. M is 1, so just v squared, plus, and remember, omega equals v over r. That's important here. Plus, because we want to get it all in terms of v, 0.016 times v squared over 0.04. Now that 0.04 and that 0.016 cancel out, and we get plus 0.4 v squared. And remember, this is all equal to 10 because we're gaining 10 joules of kinetic energy. And so this 1/2 and this v squared combined makes, I'll write it on the right side here, makes 0.7 v squared. And if you have the 10 over here and the 0.7 v squared over here, you can end up solving for it, and you get v equals about 3.78. It's 10 over root 7 meters per second. Okay, so that's one step. Next, we need to calculate the time it takes to fall. And this is quite simple. In fact, you might just know the answer off the top of your head. It's a very nice situation, but we can do the math really quickly. So remember that our projectile motions equations state that y is equal to the -1/2 gt squared, but remember, I'll write it out, gt squared. Remember, g is 10, so this is equal to -5 t squared plus our initial velocity in the right direction times time. But remember, since we rolled across this surface here, we have no y velocity. The ball has no y velocity by the time it falls off. So this is 0, and then we add the initial y, which is equal to 5, because we're starting 5 and we're going to 0. And we want to, our final y that we're solving for is when it's 0, because when it hits the floor. And so you should be able to see, if you just solve it yourself, that the time it's in the air is exactly 1 second, which is very nice. Next, we're almost there. We need to solve for angular velocity. And remember that omega equals v over r, which is equal to 3.78, plugging in our numbers, over 0.2. Perfect. So this is equal to 18.9 radians per second. And since we're in the air for 1 second, we know 18.9 radians. Okay, we're almost there. We just need to define the number of revolutions. And remember that 2 pi radians is a full revolution. So lastly, we just take this over 2 pi radians, and we get a final answer of, it's actually shockingly close to 3. It's about 3.0077 by my calculations, revolutions, which is our final answer.